In the first three sections of the chapter 5, we focused on the indefinite integral. But it is time to introduce definite integral now. The definite integral is used to compute areas, probability, average value of functions, future value of continuous income stream, and many other quantities. Initially, the concept of the definite integral may seem unrelated to the notation of the indefinite integral. There is, however, a close connection between the two integrals. The fundamental theorem of the calculus discusses this connection. Okay. Approximating areas by left and right sums. How do we find the area between the graph of the function and the x-axis? For example, this is the graph of the function f of x, 0.25 x squared plus 1. And when x change between 1 and 5, let's say this is 1, this is 5. So the area of this sheeted region how do we find the shaded area in this figure? That is, how do we find the area bounded by the graph or under the graph, bounded by the graph of f of x, 0.25 x squared plus 1, the x-axis, and the vertical lines, x equals 1, x equals 5. This description is usually shortened to the area under the graph of f of x from 1 to 5, from x equals 1 to x equals 5. Our standard geometric area formula, for example, area of the circle, area of the triangle, don't apply directly, but the formula for the area of the rectangle can be used indirectly. To see how, we look at the method of approximating the area under the graph by using rectangles. This method will give us any accuracy desired, which is quite different from the finding the area exactly. Our first area approximation is made by dividing the interval 0,5 on the x-axis into 5 equal parts. Each of the part has the same length. So this is 1. Okay, use different color. This is 1. This is 5. So we divide 4 equal parts. 1, 2, 3. So total length is 4. 5 minus 1. So we divide the 4 So each length is 1. Okay. So here the length of each part is 1. So this is 2, this is 3, this is 4. So this length, each length is noted by delta x. Delta x equals 5 minus 1 total length over number of the subinterval, so which is 1. We then place a left rectangle on the each subinterval. That is a rectangle whose base is the subinterval and whose height is the value of the function at the left end point of the subinterval. So this is our rectangle for the first case. For the second one, this is our rectangle. For the third interval, this is our rectangle. For the fourth interval, this is our rectangle. So these are left rectangles. And similarly, we can show that the right rectangle. But first of all, let's calculate the area of the left rectangle. So what is the area of the first one? We denote by the L4. We will calculate the summation of the 4 left rectangles. So the area of the first rectangle is 1 unit. This is 1 unit. So what is this length? We should calculate for x equals 1. This is 1.25. So 1.25 times 1 plus. For the second one, base is 1 unit. So this length for x equals 2. 2 square is 4. 4 times 0.25 is 1. So this is 2. Okay, let's write. Okay, also let's show that this one. 0.25 times 1 square plus 1. This is the height of the first rectangle times base of the first rectangle plus for the second one 0.25 times 2 square plus 1 times 1. For the third one, for x equals 3, this is length. So for x equals 3, 9 times 0.25. 0.25 times 3 squared, square, plus 1 times 1. Plus for the last one, this one, for x equals 4. 0.25 times 4 square plus 1 times 1. Okay. Here, this is f of 1 value, this is f of 2 value, this is f of 3 value, this is f of 4 value. You can evaluate the depth values and you will find the result as at 11.5. And by similarly, we can consider right sum. By consider the right end point of the each sub interval. Okay. So let's quickly show that situation. This point is 1. This point is 5. So for each subinterval, 2, 3, 4. For the first one this is our rectangle. So this is not by the R4. So f of 2 times 1. This length is f of 2. For the second interval, that 1. So this is f of 3. So plus f of 3 times 1. For the third interval, that point is f of 4 plus f of 4 times 1. And for the last interval, this is f of 5. So f of 5 times 1. So by using the area of the rectangle, we can approximate the area. Of course, here, by this summation, we calculate this area. Okay, so this part is extra part. These parts are extra parts. These parts are extra parts. Okay, of course, the exact area is this area. But if the number of the subinterval sufficiently large number, you can approximate the exact one. So here, this is missing parts. This is missing part. This is missing part. This is missing part. This is missing part. Okay. So this area L4 is less than the exact area. In this calculation, this is bigger than the exact area. This is just an approximation for the our area. If the number of the subinterval increase, the error became decrease. Okay. In your textbook, you can find the sum calculation for L of 16 for the 16 subinterval. So that means delta x equals 5 minus 1 over 16, which is 0.25. The calculated value is 30.59. And for the right hand point, the calculated value is 15.0.9. So from here, the exact area between these two values. For the 100 number, for the 100 subinterval, so L of 100, which is calculated in your textbook as a 14.214. So exact area between this value and the right sum of for 100 value, that is that value. So by this way we can approximate the area under the function graph. Okay, you can find more detail in your textbook. Of course, all this calculation are approximate calculation and include some errors. If we take help from the limit, we can find the exact value actually. So there is a theorem in your textbook you can find. If f of x bigger than 0 and if it is either increasing on the interval AB or decreasing on the interval AB, then it is left and right sum approach to same real number when n goes to infinity. The number of the subinterval goes to infinity. Actually, mathematicians know if function is smooth, the smoothness includes some details. Always this is correct. We can omit the increasing or decreasing cases here. Okay, but mathematical concept a bit advanced when with this explanation. We can write this mathematical explanation as stated in your textbook as a theorem. If f is a continuous function on the closed interval AB, then the Riemann sum, this sum called the Riemann sum, the left sum and the right sum altogether is called a Riemann sum. The Riemann sum for f on the closed interval AB approach a real number limit I when n goes to infinity. Actually, Riemann sum includes more than the left sum and the right sum. For the Riemann sum, generally we choose any sample point on the interval, not the left hand point or right hand point. We choose the any sample point. Okay, left hand point and right hand point are the some simple case. Okay, let's try to explain on the this graph. This is the point, first point x0. Okay, this is the A. This is the point B. This is the xn. We divide the n subspace. Okay, so this is x1. This is x2. Blah blah blah. This is xn minus 1. So for the each subinterval, we choose the arbitrary point C1, sample. It's called a sample point C1, for example. So for this case, this is the our triangle. So our rectangle. Sorry. Here, this is the C2, for example. So this is our rectangle. And for each interval, you choose the one of the C n sample point as the height of the rectangle. And from here, delta x is b minus a over number of the subinterval, and the Riemann sum can be written as the following form: f of ck is the height of the rectangle times delta x, the summation of that one from 1 to n. So this is the known as a Riemann sum. You can denote by the S, okay? So this is generally denoted by the S sub n in general. Then now we can define the definite integral. So let f be continuous function. Okay, let f be a continuous function on the interval AB. The limit, as we said here, this continuous function in that case, Riemann sum for the f approach a real number L, limit I. So this limit I of the Riemann sum for f on the enclosed interval AB granted to exist by the theorem. This theorem, okay, is called definite integral of f from A to B. So here the limit I is called the definite integral of f from x equal A to x equal B, and it is denoted by the following one. So I equals integral from A to B f of x dx. The integrand is f of x. Here this is called the integrand. The lower limit of integrand is a. This is lower limit of integrand, and this is the upper limit of integrand. So here you can consider this definite integral as a limit of the Riemann sum. So generally you can see this equals limit n goes infinity, summation from 1 to n, this summation goes infinity, f of Cn. Cn can be left hand point, right hand point, midpoint, or any point between the each subinterval, and delta x. Here delta x is b minus a over n. So, but never we will calculate the right side of this equation. We will calculate this limit to calculate the integral. Of course, we will take help from the indefinite integral. Okay. So, because definite integral is definite as the limit of the Riemann sum, many properties of the sum are also properties of the definite integral. So note that the properties 3 and 4 are similar to the indefinite integral, which is given in the section, first section of the chapter 5. Okay, and we can give some other properties. Okay, let's write the properties of the definite integral. So, properties. First property is from A to A, from the area you can obtain easily. B is A, so there is no area, so which is 0. The second property is from A to B, f of x dx. Maybe you can not consider the area as a negative value, but from A to B, we focused on the region. So from B to A, it represents the negative area. So which equals minus from B to A, f of x dx. And some key times f of x, geometrically you can obtain from A to B dx equals key times from A to B f of x dx. Here, key is a constant. And the fourth property is from A to B, summation of the f of x or differences of the f of x g of x dx equals from A to B f of x dx minus plus from A to B g of x dx. Okay, and last one, from A to C, f of x dx integral equals from A to B f of x dx plus from B to C f of x dx. Again, by the geometry of the area, you can obtain last properties easily. Okay.